Welcome back. This topic, a big topic, an important topic, the chain rule. It's all about what to do when we have compositions of functions. And yet it's also somehow so much more than that. Let's jump right in. I think the first thing to do is show you an example, and then we'll try to write out a formula for it, and then I will probably just talk a whole lot about how cool it is, how important it is. Okay, so if I have a function like y equals x squared minus 1 to the fifth, you might notice that there is an inner function and an outer function. So the inner function is x squared minus 1, the outer function is stuff to the fifth. So this is a composition of functions. We could, if we really wanted to, multiply this out, foil, 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 or use something like Pascal's triangle. We really don't want to do that, and besides, this is just a first example to show you the way. So the chain rule tells us what to do when we have a composition of functions, an inner and an outer function. So let's go ahead and see what it does. It says, look at that outer function. Look at that stuff to the fifth. What do you normally do with stuff to the fifth? And it says, oh yeah, I know. I bring the 5 down, and then I lower that 5 by 1 in the exponent. That's how I deal with stuff to the fifth. And what the chain rule tells you is leave the inside totally alone. Okay, that's telling you where you're taking that derivative of stuff to the fifth. However, that inside is also changing. And because the inside is also changing, it's going to affect the rate of change of the whole function. It's going to multiply it. What's it going to multiply it by? The derivative of the inner function. So the derivative of x squared minus 1 is just 2x. And that's it. That's the chain rule. So what did we do? We left the inside alone and took the derivative of the outer function, and then we multiplied that by the derivative of the inner function. It's kind of like, and this is a terrible metaphor, it's kind of like if you have a system of gears, the inner function is just adding another gear. And if you know how gears work, they multiply together, right? They're changing how fast things are spinning. So when you add more gears, you're changing the rate of speed that is going into the next gear. How much? Well, by however fast that inner gear is changing. Okay, this takes usually lots of practice, but let's write it down once. If f of x equals small f composed with small g. So the inner function is g, the outer function is f. Way back up here, the inner function was x squared plus 1. The inner function was x squared plus 1. The outer function was x to the fifth, right? And we're composing them together. How do I take the derivative of something like that? Well, I'll tell you. You take the derivative of f, and then you leave the inside alone, and you multiply that whole thing by the derivative of the inside. That's it. That's what we just did. It's super important. It has a lot of implications. It's how a lot of fancy analysis and fancy symbols come about, especially when you get into lots of variables. And even in just like our next two sections, we'll see it pulling so much weight for us. All right, let's go ahead and do another example. Let's look at this sine of square root of x. So hopefully you can see that there is an inner function and an outer function. The inner function is the square root of x. That's playing the role of this g. The outer function is sine. That's playing the role of this f. See if you can do it on your own. I'm going to keep playing this color game here. The derivative of the outside is cosine. Oops. Keep that purple, right? The derivative of the outside is cosine. Leave the inside alone. The derivative of the inside is, what's the derivative of square root of x? Well, there's a couple ways to write it. I'm going to go ahead and write it as 1 over 2 root x. And here parentheses are your friends, brackets are your friends, because there's a lot of multiplying happening. Great. That's it. Once you get to do it, it comes pretty fast. It takes a lot of thinking at first. One of the things you're going to need to get good at is recognizing when is there a secret composition of functions? When is there a secret inside and outside? All right, take a look at those, stare long and hard, try to make sense of them. I'm going to go ahead and move on to some notation that I don't necessarily expect you to memorize per se, but I think it's really helpful. So we could write this a different way using Leibniz notation. We could say, hey, I've got a function y, and it is f of u. and that u is actually a whole nother function in terms of x. That's pretty much the same thing that's happening up here. I've just expanded it out. But what I really want to know is what is the derivative of y with respect to x? And if you've got lots of variables flying around, this is really important to say, yeah, I want the derivative of y, but with respect to what other variable? All right, so what Leibniz notation tells you, Leibniz was a smart dude. He spent a lot of time thinking about how to make notation help and work for you. So Leibniz notation tells you that dy dx is equal to dy du, the derivative of this y function with respect to u, times du dx, the derivative of u with respect to x. Or in other words, the second part here, the second part is really just g prime. And this part is what you'd get if you took the derivative of f and just plugged in u instead. Really nice. Why is it so nice? I mean, look what you want to do. You immediately want to cancel those du's. It looks like multiplication, and in some real sense it is. And so nice, so helpful. It's really just saying, all right, it's the change with respect to u times the change of u with respect to x. They just multiply through. There's something very fundamental about composition's relationship to multiplication. Right. A little bit more before we do some more examples. Why does this work? Here is a really bad proof. So if I think about the slope of a secant line, it's the change in the y over the change in the x. Delta y over delta x, I know you chemistry folk use that all the time. Well, I could just rewrite this, thinking about the same notation as above, as the change in y over the change in u times the change in u over the change in x. And then in the limit, I hope that makes sense. That really is multiplication there. That's not like secret notation multiplication. In the limit, these are going to go to dy du times du dx, and that is exactly what Leibniz said, and that is the same thing as our chain rule written out longhand above. Super neat. Why is this a bad proof? One, I barely wrote anything. Two, you'll notice here that I'm dividing by delta u, and that delta u might be 0. And if that delta u is a 0, we'd have to do more work. So this is more of like a sketch to maybe convince you that, yeah, this is true. There's several nice proofs around, depending on how you want to go about doing it. I think I'm going to leave it there in terms of the proof, just enough to maybe convince you, yes, this makes sense, yes, this is true. But probably the first thing you should do is a couple more examples, and then go back and reread that definition and see if you can make sense of it. So we will start right in next time with a few more examples. Actually, no, let's just do it right now. Why not? Let's do this example. E to the tangent of x, can you recognize the inner and the outer function? Well, the outer function is e to the stuff. The inner function is this tangent of x. So what do? What is the derivative of e to the stuff? Well, it's e to the stuff. That whole thing times, what is the derivative of stuff? In this case, is tangent of x. So what is the derivative of tangent of x? That is secant squared of x. That's it. Easy peasy. I mean, easy if you know all the steps. Eventually it'll be easy. Right now it might still be confusing. Okay, let's do another one. Let's see why the chain rule is called the chain rule. What is the outermost function here? Sine of e to the 3x. What is the outermost function? So it looks to me like the outermost function is this sine of x. So I'm just going to go piece by piece. Don't try to find the whole thing at once, just one piece at a time. I have a cosine of, leave everything else alone. If you want to, go ahead and do some brackets. They're your friends. So that's my first chunk. Next up, I need to worry about everything on the inside. Great. What is the derivative of e to the 3x? Oh my gosh. That is another composition of functions. But I can still do it. I know how to take that derivative. So forget everything but e to the 3x. That has an outer and an inner function. So what is the outer function? Well, it's e to the stuff. So I'm going to get e to the 3x because the derivative of e to the stuff is e to the stuff. And then I need to multiply this all by that derivative of 3x. I think I know how to do that. The derivative of 3x is just 3. That's it. I mean, clean it up if you want. If you want to rewrite this as 3 e to the 3x times cosine of e to the 3x, it looks a little nicer, but not that much nicer. It's called the chain rule because we could have as many inner functions as you want. We could have as many terms as you want. We just kind of keep on going. After a while, you don't really need the colors. I just find them nice at first. But do feel free to use brackets. They can be really helpful in keeping your work straight and also keeping your brain straight, right? To kind of cue your eyes and your brain, which chunk am I working on right now? That's it for now. We'll do a few more examples and then win a prize next time.